The James Webb Space Telescope has revealed the secrets of Earendel, the farthest star ever discovered in the universe, lying at the edge of time. Earendel is so far away that its light has taken 13 billion years to reach us through a cosmic coincidence of line of sight. But this doesn't mean that it's 13 billion light years away. The proper distance of this star, which also considers the universe's expansion, is about 28 billion light years. Also, if the Big Bang theory is correct, this means that we're actually looking at a star that existed within the first billion years of the universe. Hence, it could belong to the elusive first generation of stars that astronomers have been hunting for decades. But Earendel is so far away that it's impossible to study its properties in detail with Earth-based telescopes or even the Hubble Space Telescope. And this is where the James Webb Space Telescope comes into the picture. So how did astronomers discover Earendel, a lone star so far away in the cosmos? How is it different from the stars we observe in the local universe? Finally, and most importantly, why were astronomers surprised by the James Webb Space Telescope observations of Earendel? So far, the smallest objects observed at these distances were star clusters, all inside faraway galaxies. But Earendel is different. It's the first single star we've seen within the first billion years of the universe. Astronomers found it by chance using the Hubble Space Telescope. Hubble first observed the star's parent galaxy that was gravitationally lensed by a cluster in the foreground. Massive astronomical objects, such as galaxy clusters, distort the space-time fabric around them. As a result of this distortion, the light from the foreground celestial bodies bends when it passes close to these massive objects. Sometimes, if things line up just right, this can make the light from far-off stars look much brighter than it is. Because of this bending, called gravitational lensing, the galaxy where Earendel is looked like a bent line, which scientists named the Sunrise Arc. But they saw something very bright in that bent line or the arc. Luminous sources in distant galaxies tend to be highly energetic events, such as novas, supernovas, or tidal disruptions caused by black holes. These are transients that happen to change their brightness with time. However, Hubble's observations showed that the brightness of this object remained constant for over 3.5 years. Astronomers also determined the object is magnified by a factor of at least 4,000 and thus is extremely small. Hence, they concluded it was a gravitationally lensed bright star in Sunrise Arc. Hubble couldn't tell us everything about this faraway star because of its limits. So scientists used the James Webb Space Telescope to learn more about Earendel. And here's what they found out about it. There are 3 significant points to note in the observations by the James Webb Space Telescope. The first is the star's redshift. Redshift helps us understand how far away objects in deep space are. We use a value called z to represent redshift. When z equals 0, it means it's happening now. As z gets bigger, the farther back in time an object is, and the farther away it is from us. The new Webb observations tell us that Earendel has a redshift of 6.2. This matches what the Hubble Space Telescope found in early 2022, making Earendel the star with the highest redshift ever seen. The previous record holder for the most distant star was detected by Hubble and observed around 4 billion years after the Big Bang. Another critical thing revealed by Webb is Earendel's bolometric magnitude, or how much energy it releases across all the different kinds of light. The Webb data rules out the possibility of Earendel being a low-mass star, a brown dwarf star, or a free-floating exoplanet that got gravitationally lensed. Instead, the information shows that it's a B-type star, with a surface temperature between 13,000 and 16,000 Kelvin. Stars in the universe are sorted into 7 main groups based on how hot they are: O, B, A, F, G, K, and M. A simple trick to remember these groups is with the phrase, "Oh, be a fine girl, kiss me." The problem lies when we calculate the total luminosity of Earendel. It turns out to be somewhere between 600,000 and 1 million times brighter than our Sun. This means that if Earendel is a single star that is evolved, it must be about 40 times heavier than the Sun. But there's another way this much light could be produced. It could come from 2 stars, each about 30 times heavier than the Sun, or from 5 stars, each around 20 times heavier, if they had a surface temperature of about 15,000 Kelvin. Researchers note in their paper that a single star solution is one of many that can explain the spectral energy distribution plots. Massive stars we see around in the local universe often have companions and frequently have more than one companion. While the primary companions lie within 2 astronomical units of the star, the tertiary companions can be as far as 20 astronomical units. This means that even if Earendel has companion stars, they cannot be seen by the James Webb telescope because of the resolution power. However, the second round of observations based solely on the colors of Earendel has shown that it does have a cooler, redder companion star. This light has been stretched by the universe's expansion to wavelengths longer than Hubble's instruments can detect, and so was only detectable with Webb. A companion's presence solves another problem and shows that our understanding of stellar astrophysics is on the right track. That's because if Earendel had a luminosity 1 million times that of the Sun, it would have exceeded the Humphreys-Davidson or HD limit. The HD limit is the empirical luminosity limit above which no stars have been observed, at least in the local universe. Webb's latest NIRCam observation also reveals other exciting things in the Sunrise Arc, the most highly magnified galaxy yet detected in the universe's first billion years. It shows us features like young places where stars are being born and older groups of stars that are as small as 10 light-years across. On both sides of the spot where the magnification is strongest, which goes right through Earendel, these features are matched by how the gravitational lens bends the light. The area where stars are forming looks stretched out, and it's thought to be less than 5 million years old. There are smaller dots on either side of Earendel, and there are 2 images of an older star group, probably around 10 million years old. Astronomers determine this star cluster is gravitationally bound and likely to persist until today. This shows us how the globular clusters in our own Milky Way might have looked when they formed 13 billion years ago. The discovery of Earendel is a big deal because it might be the first time we've seen a population 3 star, something astronomers have been trying to find for many years. These are stars from the very beginning of the universe. Initially, primordial nucleosynthesis produced only 2 major chemical elements, hydrogen and helium. The first stars, called population 3 stars, had very few other elements, which we call metals in astronomy. Most of these population 3 stars are believed to have died already, and the few left are hard to see because they're dim. They're almost impossible to spot naturally, and most candidates have been found in gravitationally lensed galaxies. Astronomers expect that Earendel will remain highly magnified for years to come, so subsequent observations of this far-flung star by the James Webb Space Telescope would reveal its precise nature. Looking for the first stars and galaxies has been a holy grail in astronomy. The discovery of the first generation of stars would help us understand star formation and verify the predictions made by the Big Bang model. It could even help us solve the JWST early galaxy problem, which asks why Webb is seeing so massive, fully developed galaxies in the baby universe. Also, searching for these stars is like searching for our own origins. As Richard Feynman once said, the most remarkable discovery in all of astronomy is that the stars are made of atoms of the same kind as those on Earth. This concludes another episode of the Sunday Discovery series. Recently, the James Webb Space Telescope found signs of the first supermassive stars at the edge of time. They are so huge that they could dwarf the largest stars we have observed so far. If you missed this episode, be sure to catch up on the exciting discovery.